Greetings and salutations. Welcome to the video lesson for 4.2. We're going to be multiplying radical expressions. We're going to start with just monomial radical expressions and then look to see how we can apply distributive property to that. But the basis of how we proceed lies in the commutative property of multiplication, which basically states this. You can move things around. The order shifts. We have a times b is equal to b times a. That moving around is the commutation of the factors in that product. And there is also actually a little bit of an associative property, which says if you have a times b, which gets multiplied by c, that's the same thing as a times the product of b times c. And the combo of those two properties allows us to really write this in any order. Again, this was the associative property. It's what allows us to say something like A, B, C, D is the same as A, B, D, C, which is the same as A, C, B, D, and A, C, D, B. And all those possible options of reordering all the factors. That's always allowed with multiplication. When we get to cases like this, that is in essence what happens, because in a sense, seeing 2 times root 7 being multiplied by 5 times root 3 means that we can reorder these factors. We can say that we've actually got 2 times 5, and that's getting multiplied by root 7 times root 3. That's the idea behind what happens here. That's why we're allowed to do the things we're about to do. The short of this is that we're going to be multiplying the coefficients together, and we're going to be multiplying the radical components together as well. And then the way we combine those radical components is through essentially a power law, which says that since these indices are the same, we can just multiply their radicands. So for the short form of this, we just have 2 times 5 gives us 10, and the square root of 7 times the square root of 3 is the square root of 7 times 3, so that's square root of 21. This is a final result. This is the amount of work you have to show for a question like this. We can tackle the next one similarly. We've got negative root 5 times 8 root 6. In terms of the coefficients, we're looking at a negative 1 being multiplied by 8. So here we've got negative 8 as the whole number component here. And then as radicands, we have 5 and 6, both underneath radicals of an index of 2, so we can combine them. 5 times 6 is 30, so we've got the square root of 30, and this one is done. So that's kind of all there really is to it for multiplying two monomial radicals. We do have to note that in the process of multiplying the radicals, it is possible that the radical component is not in simplest form, and we see that in example C here. We have 3 root 10 times 5 root 2, which gives us 15 from the 3 times 5, and then the square root of 20 from the 10 times 2. This 20 is not in reduced form. We see that we can reduce that. We've got 15 times the square root of 4 times the square root of 5, which, if we want to write it, is 15 times 2 times root 5, which all in all gives us 30 root 5. So we do just need to make sure we're paying attention to whether that radicand has a square factor, or depending on the index we're taking, if it's an index of 3, that it has a cube factor, so on. Just making sure that it can't be reduced any further, that it is in the best possible form. There is another way to start looking at something like this that can make things more efficient should you choose to use it. If we look at 3 root 10 times 5 root 2, we can just as well say that that's 3 times root 5 root 2 being multiplied by 5 root 2. And we've just taken the root 10 here and split it up into root 5 times root 2. The reason why that helps is because we now have a couple of root 2's swimming around. And if we reorder things again, we have 3 times root 2 times root 2 times 5 times root 5. So making sure all the components that were there initially are still there. The 3 is still there. The root 5 is still there. These root 2's are still there. And this whole number 5 is still there as well. And where that helps is, as kind of alluded to, we've got these 2 root 2's, and when they get multiplied, they just give us a straight up 2. So in the same way, we still get to 3 times 2 times 5 root 5, which still gives us 30 root 5. You can really proceed whichever way you want. Sometimes, for me personally, I'll prefer to break up the radicands if I see in advance that they have something in common. If I don't, I might start having to play with very large numbers, and it can be hard to break those back down. So if I see right away that they do have a common factor in those radicands, I might consider just going with this method instead. World's your oyster. You can certainly pick and choose. Quick, try this next example. Pause the video if you need to, but go ahead, try this one. You can try both methods, really. See if you have a comfort level with one over the other, or if either works for you. But I do suggest trying both. So pause, try it, and then come back. Oh, hopefully you paused. Looking at this, I can see we've got negative 20 times the square root of whatever 6 times 15 is, which would be like 60 plus 30. That's 6 times 10 plus 6 times 5. So looking at a root of 90 being involved here. And I know that the root of 90 for sure has a 9 in it. So I'll reduce it as that. We can throw in this bonus line saying that root 9 is actually 3, thus giving us negative root 60 root 10. And if you tried playing with this the other way, you might have said that we've got 4 times root 3 times root 2 times negative 5 times root 3 times root 5, noting here that 6 and 15 share a common 3. So I don't really need to actually figure out what 6 times 15 is, because this rearrangement allows me to say I've got 4 root 3 times negative 5 times root 2 times root 5. Once again, making sure that the 1, 2, 3, 4, 5, 6 components there match up with the 1, 2, 3, 4, 5, 6 components I have in that next line. A lot of moving parts. Make sure you're keeping track of all of them, because it can be very easy to lose something along the way. So it's a quick little double check you can do. How many parts did you have before? How many factors? How many factors do you have after performing this step? In any case, we can proceed here. We've got 4 times 3 times negative 5 times root 2 times root 5 is root 10. And then final step, we can just combine all these things. 4 times 3 is 12. 12 times 5 is 60 with a negative there, so negative 60. And the root 10 is just a straight up root 10. That's the basis of multiplying radical expressions. And again, this was just monomial times monomial. If we scroll way over to this next page, we see some monomial getting multiplied by a binomial. We know this expression here has 2 terms because terms are separated by addition or subtraction. So subtraction in this case. It's really just as the same as if we had x times, I don't know, a minus b. That we would have to see this distributive property come into play. So whatever's outside has to multiply every term in those brackets. So we'd have x times a and x times this negative b. In the same way, we have to distribute this 2 root 6 to each of these terms. So 2 root 6 times, let's do it this way, times root 2, and 2 root 6 times negative 2 root 3. So the separate multiplications get performed. The first one is 2 root 6 times root 2, and we can write that as 2 root 12. The second one, following this line, is 2 root 6 times a negative 2 root 3, so that's going to be a negative for sure. 2 times 2 is a 4. 6 times 3 gives me a radicand of 18. Boom diada, done. Just kidding. We should make sure that those two little radicals there are in the best possible form. And they are not. So we take a moment. We reduce this. This is like 2 times root 4 times 3 minus 4 times root 9 times root 2. Selecting the 4 here because it's a factor of 12, that's a square. Selecting the 9 here because it's a factor of 18, that's a square. That's just using our entire to mixed radicals strategies. 2 times root 4 is 2 times 2. The root 3 is just root 3. 4 times root 9 is 4 times 3, so that's 12, and root 2 is just root 2. And now that we've tried this one, I dare you to try this next one. If you're feeling extra daring, you can try the other two on this page. Up to you, but pause right after the sentence ends, try example F, and then resume the video. And here we are. So we're going to distribute again. If it helps you to put these arrows in here to keep track of things, then I suggest doing it, just to make sure everything's covered. You do ideally want to get to a point where you can kind of see that arrows aren't necessary, but if you need them for now, then use them. But try and get yourself to a point where they're less necessary. And you can try doing some questions without putting them in there. See what happens. Here we have 4 root 5 times 3 root 10, which is 12 root 50. And then 4 root 5 times, well, this is just a straight up 2, no radical component. So that'll be plus 8 root 5. One of these things can get a little reduced, so we do that. We've got 12 times root 25 times root 2 plus 8 root 5. The root of 25 is 5, so taking 5 and multiplying it by 12, we get 60. And then 8 root 5, there's nothing we could do with that. So this is all done. We note, don't forget that we can't go any further with either of these cases because there are no like terms to play around with. Different radicals, they have same index but different radicands, so they are not like terms. Similarly here, these have different radicands. These are not like terms. We're not going to write something like 68 root 7 because that's a hard no. Avoid that. So only add or subtract when you do have like terms. In these other examples, we do have to use a double distribution. And this is kind of just like if we had, say, x plus 1 times 2x minus 3 or something. That we might have used the acronym FOIL, but it's essentially that every term in the first binomial has to multiply every term in the last binomial. And that applies for higher order polynomials too. If you've got trinomial times trinomial, the principle still holds. Everything in the first factor, multiplies everything in the second factor. So here we've got 2 root 2 times root 6, which is 2 root 12. We've also got 2 root 2 times 2. And that's just, or times negative 2, so that's negative 2 root 2. And then we've got negative root 3 times root 6, so that's negative root 18. And then finally, we have negative root 3 times negative root 2, so that's for sure positive. And we're looking at 2 root 3. None of these terms really appear like a radicand of 12, of 2, of 18, of 3, but we do have to reduce them just to make sure everything's in best possible form. So 2 root 12 is 2 root 4 root 3. 2 root 2, no reductions happen there. Root 18 is root 9 times root 2. And 2 root 3, nothing we can do there either. Just to make sure my 3 looks like a 3. And simplifying this a bit more, 2 times root 4 is 2 times 2. Root 3 is root 3. 2 root 2, we didn't do anything to that. Root 9 is 3. And 2 root 3. Oh, what do you know? All of a sudden, some like terms are popping around. So we've got negative 2 root 2 and negative 3 root 2. We also have 4 root 3 and a positive 2 root 3 over there at the end. So now we'll want to combine any like terms. Again, this 4 root 3 combining with this 2 root 3 and this negative 2 root 2 combining with this negative 3 root 2. Thus getting us a total of 6 of these root 3s. And for the root 2s, we lost 2. We lost another 3 more. We lost 5 root 2s. Take a moment. Try this example H over here. Same as done the other one. So once the sentence is finished, pause the video, resume, see what happened, and then keep a record of your work. If it's correct, wicked. If it's less correct, keep it written there. Note, like literally write down where any errors or discrepancies occurred, just so you have that record. You know kind of what to look out for. So pause. Well, assuming you paused, we're back. So first product here is 5 root 10 times 5 root 2, which is 5 root 20. Making sure that radical sign covers the whole radicand. 5 root 10 times 2 is 10 root 10. Negative 1 times root 2 is negative root 2. And negative 1 times 2 is just negative 2. Okay. One of these can get reduced for sure. So we've got 5 times root 4 times root 5. And the other radicals don't have any square factors. And that whole number is, well, as good as it can be. So that's just getting left that way. 5 times root 4 is 5 times 2. So that's 10 root 5. We still have the 10 root 10. We lose, whoopsie daisies, root 2. We lose 2. This one is done. This root 5 doesn't have any like terms. This root 10 doesn't lead us to any like terms. Neither does this root 2, nor does this whole component. So none of those can be combined. And if you are unsure as to why that is, make sure you ask as to why that is. Why do we not have any like terms? So just repeating, to have like terms, we do need to have the same radicand with the same index. None of these happen to have that. Oh, if I look ahead here, yep, that is the end. Sweet. Well, that's been really exciting. I would recommend doing the practice work, play with the worksheets. If you need textbook work to play with as well, I can suggest some of that to you. Just let me know. And again, if you have questions, please make sure those are voiced or typed out. However they are communicated, make sure you do communicate that you have those questions. But try out the worksheets, see what you can do. And then after you've tried them, compare to answer key and see how that goes. It has been most lovely. I hope you found this video riveting. No, wait. I should say I hope you found it radical. One joke. And until I see you again, parting remark.